Hello Year 12, welcome back. We're looking at mass spectrometry today. You have done a little bit of mass spectrometry before, but we're going to look in a little bit more detail at a new kind of mass spectrometry called high resolution mass spectrometry. So here we go. Right then. So hopefully you've looked at mass spectrometry before and you remember it's all about trying to identify compounds, elements, isotopes, and it uses information about their mass. Now, typically a graph from a mass spectrum looks like this. We get this relative abundance here and these MZ values, mass to charge ratio that is. And you can see I've got a number of peaks here. This one at 35, this one at 37. This one at 35 looks to be at about 75%. And this one at 37 looks to be at about 25%. Well, that could be looking at two different isotopes. And we've got the abundance of each isotope, remember, version of an element with the same number of protons but a different number of neutrons, and if we change the number of neutrons we get a different mass. So this chlorine here has 2 more neutrons than this chlorine, so it's heavier. But there's less of this particular isotope of chlorine. You could use this graph as well to calculate the relative atomic mass. Remember your definition for that, the mean mass of an atom of an element compared to 1/12 the mass of a carbon-12 atom. Because remember, carbon by definition has a relative atomic mass of 12 exactly. So you could take these values from the graph over here, 75% at 35, 25% at 37, multiply by the percentage as a decimal, add it all up, and you get your relative atomic mass there. You might also use mass spectrometry to be looking at relative molecular masses, or MRs. So if I take these two compounds here, I've got methane and I've got propane. If I work out the MR, methane weighs 16 grams per mole, propane weighs 44 grams per mole. And actually, if I ran a spectrum of these two, if there was a mixture of the pair of them, then I would be able to see that I've got two different compounds on the basis that the two different peaks have different MZ values. Okay, right, so time of flight mass spectrometry. TOF stands for time of flight. And there are 4 stages to time of flight mass spectrometry. First is ionisation, second is acceleration, third is the flight tube, and the fourth is detection. But after all of that, it's not really one of the key stages, but it is something you would do, is you would analyse your sample, analyse that data, try and make some sense of it. I do want to draw your attention as well to some really great questions that AQA have put together. Not only have they done questions and mark schemes, but they've also written a whole student guide to time of flight mass spectrometry. It really is essential if you're an AQA chemistry student at A-level that you do read this guide and you do practice these questions. They are very specific on what they want when you give these answers, how you're supposed to word them. So make sure you get this done. It's not an expectation as a result of this video, but you'd be a fool not to do it. Links will be in the description down below. So let's do a bit of an overview on time of flight mass spectrometry. What you do to start with is you take particles of your substance, they're typically going to be atoms or molecules, and you're going to ionise those atoms or molecules, and you're going to form +1 ions of the atoms or molecules. Okay, so you're going to form ions of them, atoms to ions. And all of your particles are then going to be accelerated so that they have the same kinetic energy. So in other words, every single particle gets given the same kinetic energy, but that does not mean their velocity is the same. Their velocity will be very different depending on their mass. Then what you're going to do is all of your accelerated particles are going to enter a flight tube at exactly the same time. And because they've been accelerated with the same kinetic energy, but their masses are different, they're going to travel at different velocities. So they're going to pass down this fixed distance of the flight tube at different speeds, and therefore they're going to reach this detector at different times. We can use 2 equations to describe this. The kinetic energy is going to be fixed for all the particles, but where they have different masses, fundamentally mass spectrometry works on the basis that the particles going in have different masses. Where they have different masses, their velocities will be different. And you can calculate things to do with the time of flight or the distance of the flight tube, or the actual speed, using speed equals distance over time too. Just some units here for you as well. Kinetic energy in joules, mass in kilograms, very unusual. Make sure you divide your mass by 1,000 to get it in kilograms, because almost every chemical equation you've ever done, you've worked in grams. The velocity of the particle in meters per second, new way of writing, not the old GCSE way. D, length of flight tube in meters, and T, time in seconds. So let's have a look at these particles over here. Different masses. They're going to be atoms at the moment going in. They could be molecules as well, but bear in mind they're not charged, so they're not yet ions. First thing, first stage, they're ionised. two methods of ionisation. I'll talk about them in a minute. But when you ionise a particle, it always gets a +1 charge in time of flight mass spectrometry. Then what we're going to do is accelerate the particles. We're going to accelerate them so they all have the same kinetic energy, but remember, depending on your mass, that will result in a different velocity. So, there we go, look at that. Particle A hit the detector way earlier because with that fixed amount of kinetic energy and its smaller mass, it resulted in a larger velocity. Whereas particle B, with that fixed amount of kinetic energy and its larger mass, resulted in a smaller velocity or a slower velocity. Okay. Right, so let's have a look at some example questions that you might be asked related to this whole idea of time of flight and the tube itself. So we've got to calculate the mass in kilograms of a single chromium ion. And we're going to assume that the mass of that chromium ion is the same as that of a chromium atom. Well, that makes sense because when we ionise a sample, we only remove an electron. And an electron has a mass of about 1/2000th the mass of a proton, so a very, very tiny mass. So the difference in mass between a chromium atom and a chromium ion is going to be insignificant. Now, it's important to remember that a chromium atom, the reason its mass number is 52 is because if you had 1 mole of that substance, then it would weigh 52 grams. But 1 mole of a substance is this many particles of it. So 6.022 times 10 to the 23 particles, or atoms in this case, of chromium would weigh 52 grams. But we're asked the mass of one of those, only one of them. So we know that this many of them weigh 52 grams, so how many does one weigh? Well, pretty straightforward. If we ever want to work out the mass of one entity, that's either an atom, an ion, or a molecule in grams, then you do whatever the mass per mole is, so that might be atomic mass or relative formula mass, okay? Whatever the mass per mole is, divided by Avogadro's constant. And that will give you your mass in grams. So I know that this chromium ion or atom weighs 52 grams per mole. So 52 divided by Avogadro's number gives me 8.64 times 10 to the minus 23. But bear in mind, when we divide by Avogadro's number, when we were originally working in grams per mole, our answer is going to come out in grams. And this question, if you read it clearly, asks us to calculate in kilograms. Let's divide by 1000. There you go. Next question. In a time of flight mass spectrometer, the kinetic energy of a chromium ion was this number here. Calculate the velocity using the equation. Now, if you're in one of my classes, you'll know I'm always banging on about write the equation, rearrange the equation, use the equation. But just to show what values I've got here, I'm going to write the answers in, substitute them straight into the equation. Kinetic energy, here, half, 0.5. Mass, important this one, the mass is the mass of one ion. So it's this value here, and it must be in kilograms. It's not the relative atomic mass. If you put 52 in there, screwed up the question completely. So this mass is the mass of a singular ion, because that's the kinetic energy of a singular ion. Okay, so that's that mass there, that number there. And we don't know the velocity because that's what we're asked to calculate. So let's put these numbers in. There's my kinetic energy, there's my half, there's the mass. Let's simplify this, let's tidy this bit up. There we go, and there we go. Okay, so let's divide this by this. Okay, we've rearranged for v squared. Let's tidy this bit up. We've got v squared. Let's do the square root of this side. We've now got v. Slow that video down if you get a little bit stuck on the maths. Okay, little extension question over here. If the flight tube was 0.5 meters long, what was the time of flight? So we're trying to work out t, the time of flight. We've got the distance here, 0.5, and we've got the velocity from the previous part of the question. So plug in the numbers you know. We don't know t. Rearrange for t by doing distance divided by velocity. And there we go, we've got the time of flight. Very, very short time there. These ions are moving very, very quickly. Okay. I'd like to credit AQA for this. I've stolen these pictures straight from their guide. I hope they don't mind. We are using these in interesting times. So I'm just trying to speed up the rate at which I can make these videos, so I've used their image here. Okay, right, so different methods of ionisation. There are two of them, electron impact and electrospray. Here's type 1, electron impact ionisation. Okay, so what you've got to do is you've got to put your sample in. Now it's going in as an atom. That's really, really key. But it's got to go in as gaseous atoms or molecules. It's not charged yet as it goes in, but it is a gas. So it's either an atom or a molecule. That's the word we use to describe it. So we're going to vaporise that sample of atoms or molecules so that they are gases. And then what we're going to do is pass them through this little gauntlet here. Now, I don't know if you guys have seen Total Wipeout, where they have to run through that thing with all the pendulums, and sometimes they get like knocked over by the giant pendulum swinging by. But basically, this electron gun is firing high energy electrons through this gap. And if you're a gaseous sample trying to make your way through this gap, then you might get like knocked by those high energy electrons. And what that's going to do is if you get knocked by one of those high energy electrons, it's actually going to strip an electron off of you. It's going to do the first ionisation energy onto whatever that atom is. So gaseous atoms or molecules going in, those atoms or molecules pass through this, they get hit by the high energy electron from the electron gun, and that turns that atom into an ion. Here's an equation for it. So here's my gaseous atoms being hit by an electron from the electron gun. You can see now I've got a gaseous ion, so atom, ion, because it's now charged. It's lost an electron. This is the electron that went in, it got knocked by, and now we've got an extra electron because we've removed one of the electrons from the sample. This is not my favoured way of writing these. I personally just prefer to write the first ionisation energy. So gaseous atoms become gaseous 1+ ions, and then there's the electron that was knocked off of it. Okay. Right, now because you've formed a positively charged ion, a +1 ion, you've got this negatively charged plate, which is the accelerator. Remember, opposite charges attract, so if you've got positive ions going near the plate, they're going to get attracted to it and it's going to cause them to accelerate. Remember, all ions, independent of their mass, are going to be accelerated with the same kinetic energy, and their velocity is going to be a function of their mass. Okay, so electron impact ionisation, one of the key facts you need to know about it is it's used for elements and compounds with lower formula masses. So we're talking up to about a couple of hundred here. Obviously, if we go any more than like 500-600, I would say, anything sort of getting into protein or enzyme territory, then we're going to start using electrospray ionisation instead. So this is electrospray ionisation again. Here's AQA's diagram. Credit goes completely to them for this diagram. So here's an example of electrospray ionisation. Now, just want to highlight one thing really quickly. Chemists are going to be calling hydrogen ions protons. And the reason a chemist can call a hydrogen ion a proton is because of this. If we look at a hydrogen atom, it's only got one proton and one electron, no neutrons. Now a hydrogen ion, well, you've removed that one electron. So it's going to have 0 electrons, but it'll still have its remaining proton, but that's all it will be. If you remove an electron from a hydrogen atom, you've simply got a proton. So a hydrogen ion and a proton are exactly the same thing. Right, back to electrospray ionisation. How does it work? First thing you do is you dissolve your sample in a volatile solvent. Solvent means low boiling point, and the solvent you use has to be a solvent that contains hydrogen. Okay, has to be a solvent that contains hydrogen. Water, methanol, great examples. Then what we do is we inject our sample through this needle, and that creates this lovely fine mist. Now talking about this needle is positively charged needle. And that's because it's connected to the positive terminal of a whole high voltage power supply. Now by passing your sample dissolved in the solvent through the end of that positively charged needle, what it's actually going to do is generate H+ ions from the solvent and stick those H+ ions to your sample. Okay, so I've shown you it here. Here's your gaseous atoms. Remember, they're not ions to begin with. Atoms or molecules are going in the gaseous form because they've been turned into this fine mist. And there's the hydrogen ion that comes from your solvent. That's why your solvent has to contain hydrogen, because it has to be able to give up hydrogen ions to be able to put them on your sample. So gaseous atoms or molecules of your sample becoming gaseous ions, but the only reason they're ions is not because they've had an electron removed, but actually because they've had a proton put onto them. Okay, so a hydrogen ion put onto them. Then your solvent will evaporate away, but because you've made your sample positively charged, you've made it into an ion with an extra, because it's got that extra proton on it, well, it's positively charged. So you've got these positively charged AH plus ions, so whatever your sample is, plus H plus. Because it's positively charged, opposite charges attract, so it's going to be attracted to the negatively charged plate of that accelerator. Now again, electrospray ionisation, really important to note, this is only used for larger molecules, things like proteins, enzymes, maybe even DNA. Okay, so big biological molecules, that's when we're going to use electrospray ionisation. I'm not actually sure what the cutoff is for electrospray, what the MR would be for when you use it. You might want to look that up actually, I'm intrigued. Okay, so let's have a look now at acceleration and the flight tube. So depending on whatever method of ionisation you use, Both of them use the same method of acceleration for time of flight mass spectrometry. So you've got this negatively charged plate, and that attracts any positively charged ions towards it and causes them to be accelerated with the same kinetic energy. And after being accelerated, they're going to all enter that flight tube at the same time. But remember that their velocity in that flight tube will be a function of their mass. They've all got the same kinetic energy, but their velocity will be different. So your light particles are going to go really fast, so they're going to have a short time of flight, and your heavy particles are going to go slower, so they're going to have a longer time of flight. And we can use the calculations k equals 1/2 mv squared and speed equals distance over time in order to perform those calculations. Okay, let's have a look at the detector now. So the detector is a completely separate negatively charged plate. And the reason it's negatively charged is it's covered in electrons. And when your sample, your positively charged ions of your sample, hit that negatively charged plate, what they're going to do is be discharged. In other words, you had positively charged ions of a sample, but they're going to gain an electron. And by gaining that electron, they get discharged. See how it's charged here? Gains an electron. Well, it was positive, positive plus a negative, neutral. No longer got a charge, so it's been discharged. Now, when they pick up that electron off of the negatively charged detector plate, well, that's going to generate a movement of electrons on the surface of the detector plate. And the greater the movement of electrons, the bigger the current that's generated, and therefore the more ions that must have been discharged and the more ions there must have been. So that's going to be proportional to abundance. Okay, so here's my detector, and here's my positively charged ion that's been accelerated. Here it goes down the flight tube, boom, hits the detector, and it's going to get discharged. So I'm going to just show it disappearing. See how it took the electron with it when it got discharged? Right, so those electrons are now going to have to move, and the movement of those electrons is going to be a current. Okay, so they're all going to start moving about. The detector's going to realise that because it's got a wire in it and an ammeter that's going to measure that current. Now, obviously, if I get a big current, then lots of ions must have been discharged at that moment in time. So I must have had a great abundance of that particular part of the sample at that mass. Okay, so the larger the current generated due to an increase in movement of electrons, the more ions must have been detected at that particular mass. But the actual MZ value is simply calculated by time of flight. So abundance is about the size of the current, whereas MZ value, or mass to charge ratio, is about time of flight. Okay, so to put that into context, this chlorine weighs 35, so it would have had a shorter time of flight, and that shorter time of flight, all of those ions would have hit the detector at the same time. So the detector's got a timer on it, and it knows based on sort of what time, based on a certain kinetic energy, the ions hit the detector, what it should call their MZ value. So MZ value is based off of time, basically. And we've got the abundance here at 75%. Well, that's based off of the current picked up on the detector, based on how many ions were discharged, how big the movement of electrons was, how big that current was. Okay, right then. So, if you've got electron impact ionisation, then the MZ values on your spectrum are going to be the same as the actual atomic mass of each substance. So the MZ value for this peak here is 35, which means whatever I was looking at has a mass of 35. So chlorine's atomic mass is 35 for that particular isotope. So they're exactly the same because you've only removed an electron, and an electron doesn't really have a mass. So the MZ value is going to be exactly the same as the particular atomic mass. However, if I use electrospray ionisation, then the original peak I would have got on my spectrum is this black peak here, and it's coming in at 45 for this particular sample. It's coming in at 45, but because it's electrospray ionisation, 45 is actually one higher than the true value. So although you'll only get this black peak on the spectrum, it's important to note that what you're actually looking at is one lower than that. So I've done it in green here because this here is whatever it is plus a hydrogen. So if you take away 1 from that, you'd get 44, which would be the true mass of your sample. Okay, so an example here of how we can interpret the data. A sample of titanium was ionised by electron impact in the time of flight mass spectrometer. Information about the mass spectrum of these isotopes is shown in the table. So we've got MZ values of 46, 47, 48, 49. Those MZ values are going to be exactly the same as the atomic masses because I've used electron impact. And then we've got our abundance as a percentage. It's important that you check what format your abundance is in because it's going to affect the way that you calculate. You've got to calculate the relative atomic mass. So we've got to do a weighted average here and give your answer to 1 decimal place. So I've got these abundances here. They should all add up to 100%. If you're missing one, just write in the number that adds them all up to 100%. Okay, so what I've done is I've multiplied each mass, or MZ value, mass to charge ratio, by the abundance, and I've expressed each percentage abundance as a fraction. You could write it in as a decimal, you'd get the same answer. I got 47.8 for that one. Next, it's asking us to write an equation to show how an atom of titanium is ionised by electron impact. Okay, so in electron impact, remember that we've got to take gaseous atoms, bombard them with an electron to make gaseous ions, and then show the electrons that have been lost overall. So you could write this, titanium gaseous atoms plus an electron, that comes from the electron gun, forms titanium gaseous ions now, atoms to ions, plus 2 electrons. One of those electrons came from the titanium, the other one was the electron that it was bombarded with. I prefer, as I said, to write these simply as first ionisation energy. Gaseous titanium atoms go to form gaseous titanium ions. Little error there shouldn't be a plus right there. Get rid of that plus, okay? Plus an electron. The MZ value that reaches the detector first, well, things that are lighter end up with a higher velocity at that fixed kinetic energy. So the MZ value of these ions up here is going to be 46. Slightly different example here that I wanted to show you. This time we've got MZ values for something called Q. We don't know what it is, but the MZ values here are, they're all normal, but they're given as relative intensities. That means compared with each other. These aren't percentages. If you ever get any relative intensities, what you've got to do is see what these are all out of. So we've got to add all these up. So I'll add all these up and I get 41. So that means I can truly envisage this table as showing me this. MZ82 is 5 out of 41, 83 is 3 out of 41, 84 is 26 out of 41, 86 is 7 out of 41. Okay, same method as before, multiply the MZ value by the relative abundance as a fraction, and I get my relative atomic mass as 84. We're now asked to identify that element though. So what you need to do now is pull out your periodic table. When you've done that, you've got to look for the element that's closest to the value. There might not be one that's exactly it, so you've got to find which one's closest. One thing to point out as well is sometimes what they do in these questions is they say the element is in a particular group, because you might have elements that are really, really close, and it might be closer to one of the other ones, but it's not in the right group. So you've got to make sure you pick the one in the right group if they give you that information as well. So we've got to look for something that's about 84. Rubidium's pretty close. Krypton's closer though, so I'm going to go for krypton there. Okay, so if you want to pause the video at this point, if you are one of my students, you'll have been issued a Google Sheet with a template to write your answers directly into, so then you can submit them to me, and then we're going to go through the answers to that straight after pausing this video. Okay, what I'm going to do for purposes of time is simply pop the answers up and you can pause and check your own. Okay, right then, we're back. Now this is the new point, the point that links to organic chemistry more than anything else really. We're looking at high resolution mass spectrometry. So take the compound ethanal and propane. Ethanal's molecular formula, I've not written a structural formula here because I want it to be easier for me to calculate the MR. Much easier to calculate the MR of writing a molecular formula, the number of atoms of each element in an element or compound. Okay, so we've got a molecular formula there, molecular formula there. So I've got ethanal and propane. Now if I calculate the MR of ethanal, I've got two of carbon each at 12 and 4 of hydrogen each at 1 and 1 of oxygen at 16. That gives me 44.0 grams per mole. Remember, AQA students always write your MRs to 1 decimal place. If I do it for propane, I've got 3 carbons each at 12 and 8 hydrogens each at 1. That gives me an MR of 44 grams per mole. We've encountered an issue. Imagine you were analysing 2 different samples and you knew they were different things, but then you got your mass spectrum through and both of them gave a peak at 44. How would you know they were different things? Imagine you had a mixture of these 2 different substances. You might think there's only one thing there because the peaks overlay. Clearly we have an issue. And that issue is the result of us not using precise relative atomic masses. Now it's important to note that carbon has a relative atomic mass of 12.000000 by definition, okay? But any other element doesn't. okay, because its relative atomic mass is going to be the weighted mean average of all of its different isotopes. So what we've got to do instead is use some precise relative atomic masses, and then hopefully we should notice a difference between these two compounds. So here's some precise relative atomic masses for carbon, hydrogen and oxygen. Notice how carbon is exactly 12 by definition. If you ever ask why, it's by definition, it's 12. Okay, so MR of this one, 2 times the 12.0000, 4 of the hydrogens, each at that value there, much more precise value, and 1 of the oxygen at this value here, way more precise, 44.0261. Now let's look at the propane. It's got different elements in it, so therefore we're using different precise relative atomic masses, and therefore we're going to get subtly different answer here for what the MR is for these compounds. So we've got a different relative formula mass when we use precise relative atomic masses. So if we were to instead use a mass spectrometer that has much higher resolution, in other words has smaller intervals in the readings that it can take, then what we would have is a peak here for this 44.0, let's say 3, and we would have a peak here for this 44.06. And we can now see that we've got separate peaks because we're using a high resolution mass spectrometer. Okay, and a high resolution mass spectrometer is able to use these precise relative atomic masses in order to work out the difference between these two compounds. Notice how their molecular formula is different though. They do contain atoms of different elements, and this highlights one limitation of this method. If I took something like butane and 2-methylpropane, which are structural isomers of each other, okay, same molecular formula, different structural formula. To be a bit more specific, these are chain structural isomers of each other because we've altered the carbon backbone. Now, if I calculate the MR of this one at C4H10, I get 58.0780. If I calculate the MR of this one also at C4H10, I get the same value. So what I'm saying here is that you cannot distinguish between structural isomers because they have the same molecular formula. And if you've got the same molecular formula, well, all of the precise relative atomic masses are the same, and therefore the precise relative formula mass is exactly the same. That would be a nice wording there if you were asked that as a question. Okay, next task then. This is available on your Google Sheet. Otherwise, if you're not one of my students, you could just pause the video here and try and do this online. Be really careful on this question here. You need to show that. That means you need to show all your working. You always need to show your working in chemistry. Please do it. But this one really does need you to use the exact numbers here. Don't be inclined to shorten or truncate any of these numbers in your working. You need to use the exact numbers they give you because it's about precise relative atomic masses. Okay, pause the video here, give this one a go, then come back. Okay, let's go through the answers then. So, we've got to show that to 3 significant figures, a more accurate value for the MR of butane is 58.1. Well, in order to show that, I'm going to need to first write a molecular formula for butane. So there it is, C4H10 is butane, showed you that previously. Okay, that is actually needed for the mark in this one. All right, next up, so I'm going to do 4 times the carbon at that 12 value. You did need to use all of the numbers they gave you there, okay? And 10 of the hydrogen at that 1 value there. Okay, when we calculate that, we get 58.0794. I got 0 on the end there, yeah. Okay, so 58.0794, and then we're going to show that that rounds to 58.1 as 3 significant figures. Everything I have written here is needed for that 1 mark. This is how you answer questions on precise relative atomic mass. Write the molecular formula, show the working using the values they've given you, show the answer you got, and then show you rounding that to this number of significant figures that is requested. I told you about this question, why the precise relative atomic mass for carbon is exactly 12. Well, it's by definition. Carbon is 12 by definition. And this is a little recap on my last video on testing for functional groups. Draw the displayed formula of the organic product that's formed when propanal, that's an aldehyde, is oxidised by warm Tollens reagent. Well, remember, Tollens reagent along with Fellings are tests for aldehydes, and they oxidise them into carboxylic acids. So propanal is 1 oxidation state lower than propanoic acid, so we can oxidise that up to propanoic acid. Okay, video's done. So I'd recommend, if you haven't already, you do try this extra reading here and these practice questions. I'll put the links in the description down below. Do have a real good read of the mark scheme for this one as well, because it's important that you word it the same way that AQA do. Thank you so much for watching. I hope you found this one interesting and useful, and I will see you in the next video. Thanks very much.